Welcome to Lesson 2C, Respiratory System. Today we're going to talk about the respiratory system. First thing I'm going to do is a PowerPoint presentation. This is the respiratory system. You breathe in with your mouth or your nose. The air goes down through the trachea and then splits into the bronchial tubes, and it keeps splitting and splitting several times, up to about 20 times. And then it goes to these little grape-like structures that are sacs that are called alveoli. That's where oxygen absorption into the blood and then giving CO2 back to the air happens. This is the bronchial tree in a three-dimensional view. So it has all these splits, kind of like a tree. So we're going to talk about two different areas, the tracheobronchial region, or the conducting airway. These are just pipes. So there's no gas exchange going on here. This is just called the bronchial tree. So it keeps getting smaller and smaller tubes as they split into these T's or Y's. When they get real small, they call them bronchiole instead of bronchia or bronchus. This region is called the tracheobronchial region, and sometimes you breathe particles into your lungs, and these particles will come down into your lungs if they're small enough. Sometimes they will not be able to negotiate a curve, a turn, and they get stuck on the inside lining of bronchial tubes. Now these contain mucus. You produce about a cup of mucus a day. That's pretty gross, but we actually produce that much. The particles will stick there. And then there's little hairs called cilia that line the inside of these tubes, and the particles that are stuck there get pushed out of the lungs, expelled by these cilia. Here's a picture with an electron microscope. Little particles, these yellow things, and then these are the little hairs called cilia that kind of beat and push those particles up. They eventually go up to your throat and you swallow them. So every time you breathe in particles, and every time you swallow some of those particles that had been in your lungs. So that's the body's mechanism of removing those particles. Now the pulmonary region is the alveoli. When you get through all these T's and Y's and branches, you get down to the alveoli. They're like little sacs, and they contain thin membranes where gases are exchanged. The total surface area of these alveoli, if you lay them out flat on a surface, it's about, on a typical person, 100 square meters. A tennis court is 261 square meters, so it's a little less than half of a tennis court. So that's a lot of area. Now, when you get way down there in these sacs, they don't have cilia. They're still very moist. The really tiny particles can get into these alveoli. And then your body has to remove them with something called macrophage, which are a type of white blood cell. As you get these particles in your alveoli, the macrophage attack them and get them into the bloodstream, and then you basically pee them out eventually. Here's some pictures of the cross-section of the lungs, and it looks sort of like a sponge. There's lots of membranes in between. Here's another close-up picture. These alveoli aren't really sacs because they have a lot of holes in them. That's so that you maintain pressure, the same pressure throughout your lungs. But they do the job. They expand and contract when you breathe. And then these are probably macrophage here. These are the membranes where there's all these capillary tubes that exchange gases with the bloodstream. Electron microscope picture of the same thing. We'll talk a lot about particles as a type of air pollution. The important thing to remember, anything above 10 microns, micrometers, they get trapped in your nose or in the back of your mouth. So you don't get those down into your lungs. But anything below 10 microns, anything smaller, starts to get in your lungs. So you can see here 4 to 5 roughly microns are in the pharynx area, trachea. When you get down to a micron or so, these get way down into the deep recesses of the lungs. So anything below about a micron can get into the alveoli. Anything above 1 micron gets stuck in the bronchial tubes, and they get removed by the cilia. We call these inhalable coarse particles that get trapped in the tracheobronchial region, expelled by cilia when they're between 2.5 and 10 microns. About 1 to 2.5 microns get into the really tiny bronchial tubes, and then the submicron particles get into the alveoli. Here's a cross-section of a human lung. Fairly healthy. You don't see many black spots, but everybody has some particles you breathe in sometime in your life that get down in the alveoli or in the bronchial tubes where the cilia can't remove them, and that may be because of size, the shape. Macrophage can't remove them if they get into the alveoli. Things like tar from cigarettes, the body can't digest them. So you get some of these black regions. Here's a picture from an unhealthy person. You can see that approximately half of this person's lungs are covered with this black stuff. And these stay in your lungs for the rest of your life. And so that's why people that are heavy smokers, for example, if you lose half of your lung surface area, that 100 square meters of alveoli turns into 50 square meters. And that's why they have a hard time breathing. I want to write down some of the important things to remember from this slideshow. Alveoli, the surface area, is approximately 100 square meters, about half a tennis court. You produce approximately 1 cup of mucus per day. There's approximately 20 branches in the bronchial tubes. You have your trachea, and then you start branching into the left and right lungs, and then these keep branching like I showed you on those pictures. That happens about 20 times. And then finally, when you get to the really tiny bronchial tubes, you have these alveoli, little sacs. Remember that the cilia, those are hairs, and the mucus work together. The mucus traps particles, and then the cilia kind of beat and push those particles out. So mucus and cilia remove particles from the bronchial tubes, whereas you need macrophage, these white blood cells, to remove particles from the alveoli. Some particles stay in your lungs for your life. Cilia and mucus can't remove them, and the macrophage can't remove them, so things like cigarette tar stay in your lungs. Let's look at something called spirometry. Here's a definition. Spirometry is the use of instruments to measure breathing volumes and pressures. Here's an example from a spirometer. Inspiration means you inhale. Expiration is when you exhale. The first thing you can see is there's some hysteresis there, but this shows pressure on the x-axis. Plural just means lung, and then lung volume change in liters. This person has approximately 500 milliliters, or a half a liter, of volume that he or she inspires or breathes in, and then the same amount you breathe out. That is called the tidal volume. The tidal volume is the volume of air inhaled, and the same thing would be exhaled, typically taken at rest. V sub T is the tidal volume. For a typical person is about 500 milliliters, half a liter. Here's a little class demo about spirometry. This is a kind of spirometer that you might get in the hospital. This is an inhalation type. It tests how well you can inhale air, what volume and what rate. This one goes up to 2,500 milliliters. It has this little yellow flow rate meter that you try to keep between these two limits. First you exhale all your air, and then you breathe in. Set this to some target like 2,000 milliliters. See how well I do. I passed. I did way more than 2,000 milliliters, so that's a spirometer test. Here's a typical test that someone might do, a physician might do, and we'll define these things. The spirometer is measuring the volume in liters that are being breathed in and out. So when it goes up, that's breathing in, and when it goes down, that's breathing out. This is the volume in your lungs. Here's a person at rest, just breathing in and out, in and out. So what the doctor will say is breathe in as much as you possibly can till it hurts and stop. That's your vital capacity. So this person has about 7,000 milliliters or 7 liters of vital capacity. I want to point out that this is for athletes. These are like football players, so they have much bigger lung capacity than most of us. They're big guys and they're healthy athletes. So this is usually smaller, typically around 5,000 for a typical person. But anyway, this shows you the basic trend. So you breathe in as much as you can, and the doctor says, okay, now exhale as much as you can till it hurts. So you go, and then when you're finally done, you can't breathe out anymore. That difference is the vital capacity. So this person has from about 2 to 7, so about 5 liters of vital capacity. Even when you breathe out as much as you possibly can, your alveoli don't collapse completely. The functional residual volume is when you're normal breathing and what's left in your lungs. The residual volume is when you breathe out as much as you can and there's still some volume of air left in your lungs. In this case, it looks like about 1.5 liters. The functional residual volume is about 3 liters. So even when this person is breathing in and out, sitting at rest, there's 3 liters of air in his lungs when he exhales. And when he exhales as much as possible, there's still about 1.5 liters there. And so that's how this works. By the way, the total lung capacity is from when you breathe in as much as you can to 0. So that's about 7 liters. But the vital capacity, which is what you actually can do that's useful to you, in this case, the vital capacity is approximately here from 7 to 2 is approximately 5 liters. And then the functional residual volume here is about 3 liters. tidal breathing represents only about 3 to 4, so this is approximately 1 liter that this person is breathing in and out, compared to 7 liters of total lung capacity, so that's a very small percentage of your actual volume of your lungs. Now let's look at something called the Unsteady Bohr model to try to model this. We have a tube that models the bronchial tube, so this is the rigid portion, no gas exchange, and then you have kind of a balloon, which is the alveolar volume, VA, which is a function of time. When you breathe in and out, we're just letting this kind of balloon expand and contract, and then you put in a QT, tidal volume flow rate. So that's how fast you're breathing. This is at rest if it's a T. This portion here, where it's rigid, is called the anatomical dead space. Typical person, approximately 150 milliliters. So that's the air left in your lungs. So imagine when you breathe out this air that's been in your lungs, and it fills up this anatomical dead space, and then it goes out to the atmosphere through your nose or your mouth. But when you breathe in the next time, first you're going to breathe in that portion of air into your lungs. So that's kind of stale air. It's not fresh air. There's fresh air coming in from outside, but you don't get any fresh air until first you take this chunk of stale air and push that into your lungs. You breathe that in. Then you start breathing fresh air. So that's why we call it dead space. It's kind of used air or stale air that you breathe every time you take a breath. And then the volume in here actually changes with time. It's a function of time. I have another little demo video for this. I just took a tube and a balloon so that I can show you how that works. Here's a little demo of the Bohr model. We use a stiff tube here as represent the bronchial tubes, trachea, everything, all the bronchial tubes going down to the alveoli. This balloon represents the alveoli. So when you breathe in, you're going to draw air in through the bronchial tubes and trachea, everything, all the way, all those branches down to the alveoli, which we represent all the alveoli by this one big balloon. And so when I breathe in, it will look like this. I'm actually going to blow into this to represent breathing into the lung. Now pretend I'm holding my breath. Then when I exhale, it lets the air through the bronchial tubes. That's a simplified demo of the Bohr model. This is a great model because it's unsteady, and it is a good model for actual breathing, but it's a complicated model because this is unsteady and it has variable volume. You can do this model, if you want to get real fancy, would have non-uniform concentrations. So we're going to look at a simpler model, and this extended steady Bohr model is more like what you're used to in mechanical engineering, where you make a control volume. So this is just a box, a control volume, and this model is actually, we call it extended, but it's actually a simpler model because it's steady and we have a fixed volume rather than a volume that expands in and out, and we assume well mixed. So instead of non-uniform, it's well mixed, meaning it's the same concentration. If I take any place in this box, it's the same concentration or molar concentration, and it's a fixed volume instead of a variable volume, and it's steady instead of unsteady. So those three things are approximated. Here's what it looks like. We just have this box, which we'll pretend is the alveolar volume. Inside there we have a molar concentration, C molar alveolar, or you can just use a mass concentration instead, C alveolar. If you want, you can also do these things in terms of partial pressures. This V is fixed, and I'll put some typical numbers. These vary with persons, as I said. This will be approximately 3,000 milliliters or 3 liters. And then you have some inhaled air, and this is steady, so you just have air coming in and you have air exhaled or coming out. So you're going to breathe in at some QA, some volume flow rate of inhaled air with a molar concentration of air. It can be air or it can be any chemical that we're analyzing. So if we're looking at oxygen uptake, we can have that. Look at the mass concentration of oxygen or carbon monoxide or benzene vapors or whatever you want to look at. And this comes in and mixes, so we assume this is well mixed, like I said in here. And then some of that mass goes into your blood. So here's the blood. Q of blood is the volume flow rate of blood. There's partial pressures of the chemical in your blood too. This is now a liquid. Your blood's a liquid, of course. There's another little control volume here that is in the blood. So we have mass of whatever oxygen or CO or whatever you're looking at goes through the membrane into the capillary tube itself, the blood, and so the partial pressure increases of whatever chemical you're talking about. And then Y is just the distance along the capillary tube, so then oxygen and other chemicals go from the lung to the blood. So that's the extended Bohr model. And this Kb I wanted to define here as the solubility coefficient. It's the volume of gas absorbed into the blood over the volume of blood. So it's just V gas absorbed over V blood. And that's a coefficient that is important. So for example, if you're looking at oxygen breathing, so Kb for oxygen, Kb sub O2, for a typical person is 10.7 milliliters of O2 per milliliters of blood. So if you're thinking here, you say, how can Kb be greater than 1? We're putting in more oxygen than we have blood. The reason is that the O2 is a gas and the blood is a liquid. There's such a huge density difference that they're about 3 orders of magnitude. So you can fit in all that oxygen as it dissolves into the blood. And then once that oxygen gets into the blood, the O2 is attached to hemoglobin molecules which are in the blood, and then that distributes it throughout the body. When you have natural metabolism and you turn some of that O2 into CO2, and then that CO2, the same thing comes in reverse, and then the CO2 will go out of the blood into this volume, and then you breathe it out. This exhaled air will have less oxygen than was inhaled, and it'll have more CO2 than was inhaled. There's very little CO2 in the air, like 400 parts per million, but you'll exhale much greater amount than that. We'll talk about that a little bit later. So let's define a few other things here. Define QT as the tidal ventilation rate. We talked about VT, which is tidal volume. Q is a volume flow rate. So this is the tidal ventilation rate. This is all in this extended Bohr model. So it's the average volumetric flow rate of the air breathed in at rest. So QT for tidal is VT, the tidal volume, times F, where F is the breathing frequency, usually per minute. So F for a typical person sitting still is around 10 to 15 breaths per minute. And so QT for a typical person would be 500 milliliters per breath times F, say about an average of that 12 breath per minute is equal to 6,000 milliliters per minute, or 6.0 liters per minute. So you breathe in and you also breathe out. Then in a minute you breathe about 6 liters of air, which is quite a bit actually if you think about it, in 1 minute. But remember the anatomic dead space, all your bronchial tubes, so not all of this is useful, and so we'll define QA as the alveolar ventilation rate. This is what we're actually going to use in the Bohr model. You see this QA up here. So the volume flow rate coming into this extended Bohr model is what we're calling here the alveolar ventilation rate, and that's the average flow rate of fresh air. So this is the fresh air analog to the QT. So QT was just the total, but only part of that is fresh air because of anatomic dead space. So we can say that QA is the tidal volume minus this anatomic dead space volume times F. Instead of just VT times F, we have VT minus VD times F. So this is useful flow rate of air into the lungs. Typically, this would be 500 and then 150 as your dead space milliliters per breath times 12 breath per minute is about 4,200 milliliters per minute, or 4.2 liters per minute. So you compare these two, you see that you're actually getting a useful amount of air into your lungs that's significantly smaller than what you're actually breathing in because of the anatomic dead space. You can also rewrite this as QA is equal to 1 minus VD over VT, all multiplied by QT. If you just combine these equations, do a little bit of math. So the bottom line, at rest, VA, alveolar volume, that's useful, is VT tidal minus V dead space. So that's typically 500 minus 150, or about 350 milliliters of fresh air. That's fresh air that you breathe into your lungs. let me introduce another parameter here. RVP is called the ventilation perfusion ratio, and that's equal to QA over QB. So just a ratio of volume flow rate of air to the volume flow rate of blood, and this is the alveolar amount that we talked about here, the alveolar ventilation ratio, and QB is just the volume flow rate of the blood. In table 2.4 in the textbook, we give QT, VT, RVP, etc. for various levels of exercise. There's 4 primary levels of exercise. R is just when you're at rest. LE is light exercise, so like walking around. ME would be moderate exercise, so you're doing something a little more physical. And then heavy exercise would be something like running or swimming or something like that. As the exercise level goes up, what we find is that QA goes up and QB goes up and QT goes up. So you're breathing in faster, more breaths per minute. The QA is just a percent of QT, so that goes up, and your blood flow also goes up. As you exercise, you breathe deeper, so your volume actually increases, your heart pumps faster, breathe in more. But it turns out that QA increases faster than QB increases. This ventilation perfusion ratio goes up by a factor of approximately 2.6 from rest to heavy exercise. This is table 2.4 right from our textbook. You can see we have these 4 different types of exercise, and we're looking at all these properties: ventilation rate, liters per minute, frequency, that's our F, so how many breaths per minute. So I like to just compare rest to heavy exercise, and you can see that when you're at rest, your blood flow is about 6.5 liters per minute, and your blood flow at heavy exercise goes up to 21.7 liters per minute, so that's quite a bit. If you look at the air flow rate, it goes from 7.66 up to 67.66. So that's quite a big increase, about a factor of almost 9. But then RVP is the ratio of those, goes from about 1.18 to 3.11. What we often do is define an RVPM. It's a modified ventilation perfusion ratio, RVP, and that's equal to QA over QB like it was before, but we also put KB in the denominator. This solubility coefficient is the gas absorbed into the blood over the volume of blood. So we put that into the ventilation perfusion ratio to make a modified one. And so that's what we sometimes plot. For example, this figure from the textbook also. So that comes in handy. And you can see that in this case, we're looking at the uptake efficiency for oxygen. And this is a complicated plot, but what I want to emphasize here without going into a lot of detail, the problem is that the efficiency drops from about roughly 90% at rest to more like 50% at heavy exercise. So you can see that here, 85% down to 48% to be precise. RVPM increases, but not fast enough. The bottom line in all this is that since the blood rate increases more slowly than the air intake rate, it's the heart that limits exercise, how much exercise you can do. So it's not the breathing that limits your exercise, it's the heart. And as you increase exercise, going from rest to heavy exercise, the efficiency of uptake goes down considerably. And so that's why you can't exercise for a long time without getting exhausted.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.